So it's a wonderful pleasure to be here. I think I've been invited to this meeting to represent what you might call a theoretical physicist with a good attitude about the anthropic principle. By which I mean there are people who have silly, polemical, knee-jerk reactions to against even contemplating these kinds of ideas. It's possible that anthropic reasoning plays some role in understanding some aspects of our universe. And anyone who's looked at many of the strange patterns in the constants we see has wondered about this possibility on and off. And of course, there's been a wonderful tradition, especially here in the UK, of people thinking about this going back 30, 40 years. And I've certainly been brought up in this subject by reading classic papers of Carter and Rees, Barrow and Tipler's book. In fact, when I was at Harvard one year, I gave an entire class that was officially called Widely Applied Physics. Unofficially, it was Barrow and Tipler. And the point was to go through, well, but updated somewhat. The point was to go through all of physics, reducing things to fundamental constants, which is a wonderful way of learning physics, but also a way secretly for me to get more up to date on all the little coincidences and accidents in the constants that seem to be to play a crucial role in the world around us. So anyway, so I think I don't have a knee-jerk reaction against thinking about anthropic reasoning, but nor am I completely convinced that that it's being applied in the correct way to the questions that we're thinking about now. And so I want to tell you in these two lectures about my thinking about these things. And I've divided the lectures into two pieces. So today I'm mostly going to talk about there's lots and lots of circumstantial evidence for little tunings and accidents in constants, which might be anthropically necessary. But today I want to talk about the biggies, the real big ones, the famous cosmological constant problem and the hierarchy problem, and arguments for why these involve fine-tuning and the role anthropic reasoning might play in addressing them. And tomorrow I'm going to talk about the physics picture that could underlie the multiverse that will allow all these different possibilities to be realized and get us into the conundrums for trying to make proper theoretical sense of this kind of a picture. I think what I'm saying today will be more or less uncontroversial in some ways. What I'll talk about tomorrow will be a more personal take on what I think is going on in this business. Whether it's controversial or not is kind of irrelevant because no one has made any progress on trying to make any sense of this picture of a multiverse and eternal inflation to anything close to the usual standards of understanding and rigor in theoretical physics. So because there's been so much spectacular failure on this problem over the last 5, 6, 7 years, I think while what I have to say tomorrow won't push the discussion forward too much perhaps, I hope it won't push it backwards and will at least illustrate what I think the central issues are. And actually, I want to put this entire discussion, both today and tomorrow, in a slightly broader context, because they're not actually isolated. These questions about anthropic reasoning and the multiverse are not actually isolated from many of the more widely recognized central themes and questions in fundamental physics of the 21st century, which I can illustrate by comparing them with the tremendous successes we had in the 20th century. This slogan you can think of as the sort of summary of all of 20th century physics. We learned something amazing, which is that the combination of these two big principles of quantum mechanics and special relativity together imply that the structure of the laws of nature at sufficiently large distances is almost completely inevitable. There's almost no choices in what the world can look like once you know those two basic principles. It's not true if the world just had quantum mechanics, and it's not true if it just had relativity. But if you have both quantum mechanics and relativity, the long distance property of the universe is almost completely inevitable. What I mean by that is, let's say you took a bunch of theoretical physicists and you didn't let them look at the world outside. You put them in a room, you close the windows. Of course, it's all very counterfactual because the room is in the universe and so on. But anyway, imagine you didn't let them look at the world outside. You just gave them the basic laws of relativity and quantum mechanics, and that's it. And asked them to figure out what are all the possible consistent universes, what are all the possible universes compatible with these two basic principles. And you also have to imagine they're sufficiently competent. So, if you give it to me, I would give up very quickly. And I'd say, you can't do anything. This is crazy. They don't possibly go along with each other. But you give more competent theoretical physicists, and you give them time and food, and graduate students, and they will eventually figure this out, which is an amazing fact, okay? Which is, again, as a consequence of relativity and quantum mechanics, at long distances, all the interactions in the universe ultimately arise from elementary interactions between three particles, A, B, C. And there's a tiny menu of the kinds of elementary particles you're allowed to have. The allowed spins of the elementary particles, something you know, elementary particles have spin. But the allowed spins they could have, compatible with the laws of quantum mechanics, could be any integer multiple of 1/2 Planck's constant. But the allowed spins they can have are 0, 1/2, 1, 3/2, and 2. Okay? That's it. And so all of the choices that we can make about what the world looks like then reduces to what those interaction strengths are and how many of each of these guys we can have. That's it. Okay? Now, in fact, they would tell you more. They would tell you that spin 2 guy is really special. You can only have one of them. And it does weird things. If you have massive particles, it gives rise to universal attraction between all of them, makes things go around in orbits and so on. It's gravity, right? That they don't know, they haven't seen apples fall, but it's just quantum mechanics and relativity makes the spin 2 unique. And things get a little less unique as you go down the line. These guys are totally promiscuous. They can do anything. These guys are relatively promiscuous. These guys get relatively constrained. You can have at most 8 of these guys. They're very interesting. We'll come back to them in a second. But this is something that you just discover from pure thought and the basic principles of relativity and quantum mechanics. Amazingly rigid theoretical structure for describing the universe. Almost no choices. I colored in red the particles that we had seen in nature before at spin 1/2, 1, and 2. Electrons have spin 1/2, photons have spin 1, the graviton has spin 2. And we had not seen before particles of spin 0 or spin 3/2 until July 4th, 2012, where we get to turn the red into a black because we finally discovered something nature can do according to these principles that we had not seen it do before, but it could do compatible with those principles. And that's the Higgs particle. Okay? That's why the discovery of the Higgs is actually important and not just hype for newspapers. Okay? It's because it's the first time as theorists we got to do these two things, make a list of what nature can do, look at what the world does do, and find something that it can do that we hadn't seen it do before that it then does. Okay? And we got to change that red into a black. Okay, that 3/2 is still missing, and we'll come back to it in a moment. All right, so this is a remarkable fact. Incredible rigidity in the structure of the laws of nature. And our universe makes some choices for how many spin 0, how many spin 1/2, how many spin 1, and so on. Okay? And those choices are reflected in all the interactions that we see in nature that hold sway over these enormous range of distances all the way up from the size of the observed universe down to distances around 1,000 times smaller than the nucleus, which is the distances we're probing at the Large Hadron Collider today, around 10 to the minus 17 centimeters. So this is a real triumph that basic principles almost completely dictate what the world can look like. If I clean up that picture a little bit from the point of view of fundamental physics, all of the previous distance scales are from here to there, and there is an even tinier length scale, the famous Planck length, where we think gravity becomes important, quantum mechanics and gravity become important at the same time. These 3 length scales, the Planck length, this weak scale around 10 to the minus 17 centimeters, and the size of the observable universe are the main actors in the drama that I'll be talking about today and tomorrow. So that's the summary of the 20th century. We basically understand the mechanics of how the world works. It's remarkable, but at sufficiently long distances, we understand how the world works. And that means that the questions we have today are one structural level up from the questions we had 40 or 50 years ago. We understand mechanically how the world works, but we don't understand both at a very deep level these foundations on which our 20th century successes are built, and we don't understand why we got the world we got. But they're not questions about this or that particle. There are structural things about our universe. And if I had to say in one sentence what the central theoretical questions driving physics in the 21st century are, and this has nothing to do with anthropics and this and that. Anthropics will end up being a small aspect of this bigger set of questions, perhaps. But the real drama is that exactly the same principles seem to make the universe impossible. On the one hand, they make the universe inevitable. On the other hand, more structurally, they seem to make the universe impossible. And this has two aspects to it. And in a more logical exposition of these things, I would actually describe them in this order, but as befits a meeting on anthropics, I'm going to reverse the order in which I talk about them. The most fundamental problem is that the foundations are suspect. Okay? Relativity and quantum mechanics are built on the idea of space-time, local interactions in space-time, and the idea that there's a wave function that's evolving in a gigantic Hilbert space. We have good reasons to suspect that both of these things aren't exactly right. Almost everyone will tell you that space-time doesn't really exist. And this has to do with facts about both gravity and quantum mechanics. So we'll review this tomorrow, but it's almost certain that space-time is an approximate notion that has to emerge from something else. And it's even likely that questions in cosmology, not random questions about measurements or things like that, which I, like many of my friends, think there's nothing particularly interesting or exciting going on there, but there are strange things about quantum mechanics. And the strange things arise when you start trying to apply quantum mechanics to the entire universe for a variety of reasons. Okay? So there are limitations of quantum mechanics when it comes to a cosmology. So these two principles, relativity and quantum mechanics, spectacularly successful, highly suspect at a very deep level. Although you sometimes have to ask very esoteric questions in order to see their limitations, but those are the kinds of questions that we're talking about here. And a second set of questions is much more down to earth, and that's what we'll talk about at length today. Why is there a macroscopic universe? One of the most basic facts about the world: it's big. It's big despite the fact that it's made out of small things. Now, you might not think this is such a big mystery. Why is an elephant big? An elephant is big because it's made out of tons of atoms. So big whoop. Okay? But if you think about the question more and more deeply, you find that as you keep going down, we don't have a good answer to this question. We'll talk about it more. In fact, a prerequisite to having big elephants is having a big universe in which to have the big elephants. Okay? So first, the question of having a big universe. Why is the universe big? That we don't have a good answer for at all, and that's a way of talking about the famous cosmological constant problem. The essential difficulty is that the universe is big, while not only is it made of small things, but it's governed by quantum mechanical laws with more and more violent quantum mechanical fluctuations at shorter and shorter distances. With such incredible violent quantum fluctuations on such incredibly tiny distances, why is there any macroscopic correlation between what's going on here and there in the universe at all? Why do we have such enormous separations of scales when these violent quantum fluctuations seem to want to destroy it? So the question of why it's big is the cosmological constant, and the question of why it has big things in it is the famous hierarchy problem. It's a way of phrasing the famous hierarchy problem, which ultimately traces to the question of why gravity is so weak compared to everything else. Since I probably won't talk about it as I go on, let's just do the case of the elephant for a moment. Okay? The elephant is big. It's a big thing sitting on an even bigger Earth. Why is the Earth big? Well, what fixes the size of the Earth? The Earth is as big as it gets. The Earth has a size such that the gravitational pressure that wants to crush it is counterbalanced by atomic pressures that want to hold it up. Okay? So you can do a very simple estimate equating those two pressures, and you get a beautiful formula, parametric formula for the radius of the Earth. The radius of the Earth divided by the radius of the atom is precisely the square root of the ratio of the electric force to the gravitational force between a pair of protons. Okay? So the Earth is bigger than proton. You can put the numbers in your head, right? That ratio is about 10 to the 36. You can take the square root, multiply by the size of the atom, and bingo, that's about the radius of the Earth. Okay? And why is what about elephants? Well, elephants, it's no good for them to not be liquefied by the pressure of gravity. You have to do a little more than that. They would actually be in trouble if you just broke one layer of bonds in their bones. So you get the 2/3 power of that ratio. And that explains why elephants are big. Every macroscopic thing in the universe gets its large size as a consequence of the weakness of gravity compared to everything else. Gravity was not weak compared to everything else, would all be crunched into black holes, and it would be a very unpleasant universe. Okay? So these are two very basic facts about the world, and we don't have a good understanding for why we got this particular universe. So yet another way of phrasing these difficulties is going back to this picture of all the scales. So we have the size of the universe, the weak scale, and the Planck length, and we have these enormous separations between them, between the micro world and the macro world. Why? Where did these huge separations of scale come from, especially when they seem to be extremely sensitive to violent quantum mechanical fluctuations? Okay, so first at a cartoon level, and then we'll talk about it slightly more technically, what is the problem? Well, something that you all know is that quantum mechanics and relativity, special relativity, one of the early things that union predicted was the existence of antimatter, and that in turn means that even the vacuum is exciting. So if you want to probe very small distances with a magnifying glass, you put so much energy into such a small region of space that you can produce, let's say, electrons and positrons out of the vacuum. And that means that it's useful in thinking about things. For example, in thinking about an electron, it's more useful to imagine it as being constantly surrounded by this cloud of particles and antiparticles popping in and out of the vacuum around it. Of course, I don't want to have any conversation about whether it's real or not. Having that mental image is more useful because it leads you to correct ways of thinking and correct predictions about what's going on more often than if you don't have that picture. Okay, so the vacuum is exciting. And the difficulty is that it's too exciting. Even the vacuum has energy as a consequence of the uncertainty principle. If I have a pendulum a ball hanging on the end of a string, classically it can be at the bottom of the string and also not moving at all, so we can say that its minimum energy is 0. But quantum mechanically, I can't both know that it's at the bottom and that it's not moving. It has some minimum energy, and that energy is Planck's constant times the frequency of the oscillation of the pendulum. And what that means applied to the vacuum is because this energy is proportional to frequency, as I go to smaller and smaller boxes, the frequency of the oscillation in the box gets larger and larger. And so there's larger and larger quantum fluctuations with more and more energy in smaller and smaller boxes. So we can use that to make an estimate for the famous vacuum energy or vacuum energy density, the cosmological constant capital lambda. So what is this energy density? It's an energy over a volume. Naively, that energy is infinite, right? I can make the box smaller and smaller. The energy from quantum fluctuation is bigger and bigger. The volume is smaller and smaller, so the ratio is going through the roof. Okay? And for reasons we'll talk about more tomorrow, if I just make the box arbitrarily tiny, the energy density from this estimate gets arbitrarily large. There are good reasons to suspect that the whole picture of boxes and space and time and everything is breaking down somewhere near the Planck length. So perhaps it doesn't make sense to trust this estimate much past that point. But anyway, this naive estimate would give us a Planck length over a Planck volume. And that's just an absolutely enormous vacuum energy density. This energy density, because energy gravitates, would lead to curvature of space-time. And we don't need any equations to know what that curvature is, because the only word appearing in this entire slide is Planck. Everything is Planckian. Gravity is Planckian. Everything is Planckian. So the only kind of curvatures we can get from this effect are also Planckian. So either the universe would be curled up to tiny size at around 10 to the minus 33 centimeters big, or it would be explosively accelerating, doubling in size every 10 to the minus 43 seconds. That looks nothing like the world around us. And you might say, I don't trust this estimate. That's a crazy estimate. We haven't been anywhere near the Planck length. That's fine. Stop at a more reasonable energy scale. Stop at the size of electrons or the size of protons or the size of experiments that we're doing at accelerators like the LHC. You still get an answer that's 60 orders of magnitude bigger than it's allowed to be. And of course, for a long time, theorists had an attitude about this problem that, yes, this is a very severe difficulty, apparently. We have this back-of-the-envelope estimate that disagrees with experiment by 120 orders of magnitude. That's what I'm writing there. And so that means that we're thinking about something terribly wrong, and there's going to be some magical mechanism that will make the vacuum energy exactly zero. No one had the faintest clue what such a mechanism might be in any concrete sense. Okay? So it was never some sort of concrete research program. There weren't people sitting around working on the vacuum energy equals zero problem. There wasn't even a faintest idea for how it might work. But it was a sort of a fantasy for what might make the problem go away. Incidentally, theorists have had this kind of fantasy about similar problems a number of times in the past. Not for problems quite as severe as this, but in the 1930s, when the generation of Heisenberg and Dirac and Bohr and Pauli got confused with the much milder logarithmic infinities of quantum electrodynamics, they too had the attitude, these things will go away. You know, it's just some fog and mist that'll all sort of go away and we won't need to worry about it. And what crystallized people to realize they had to take these things seriously was an experimental observation. When people measured the Lamb shift, or when people measured the anomalous magnetic moment of the electron, these things convinced people there was an effect that was there. It clearly looked like it was associated with these virtual quantum mechanical effects, and it was not infinity. It was calculable and small, and you had to do something about it. Okay? And the observation of a non-zero, of an accelerating universe, which is, there's no reason not to believe at the moment that it's nothing other than a tiny cosmological constant, might be an example of something like that. Okay? So if we want to explain our accelerating universe, then the value of the vacuum energy needed to do it is 120 orders of magnitude smaller than this back-of-the-envelope estimate. It's not like we need some mysterious dark energy and we don't know what it is, and it's quite the contrary. We have no difficulty making the universe accelerate whatsoever. The problem is that it wants to accelerate vastly more quickly than we observe it to do, and the value we need seems to be ridiculously, ludicrously small compared to this back-of-the-envelope estimate. Oops. My curve is wrong here. The dot should be underneath the curve, not above the curve. Sorry about that. Okay. Now, this is what we have to do to confront the question of why is the universe big? But surely we have an answer to the question of why the universe is big. We go around doing all these fancier things, making all these fancier predictions. What the heck are we doing? When we apparently don't even have a good answer to why the universe is big. And here it's very important to point this out, and we'll talk about it at greater length. We can do something about this. We have no difficulty accommodating the fact that the universe is big whatsoever. Okay? All we do is we say there is this quantum mechanical correction to the energy density of the vacuum. There must have been a classical piece sitting there already. And if this piece, let's say in Planck units, is 2.649378 ... then it must have been that this piece is exactly opposite it, but starts differing from this guy in the 121st decimal place. Okay? Nothing stops us from doing that. That's what we do. In fact, we don't actually do this. So we don't actually have to employ generations of graduate students to calculate this to 120 decimal places. We just imagine that we did, and whatever answer they get, we say, that must have been opposite it to 120 decimal places, and starts disagreeing in the 121st. Okay? There's nothing wrong with this. In other words, it's not an inconsistency. It's not some physical or logical contradiction. We can do it, and in fact, we do it. We do it, and we proceed, and we make predictions for the g minus 2 of the electron to 12 decimal places, and we do all these spectacular things after we do this. Okay? We make the universe big, and then we go. So there's no problem doing it. But many of us feel strange about doing it. Okay? It seems like a finely tuned situation. The analogy, there's many analogies. The analogy I like to use is it's like walking into a room and seeing a pencil standing on its tip in the middle of a table. Okay? It's possible. That's a consistent configuration of pencil to be within 10 to the minus 120 degrees of vertical. But if you saw it, you would think there's probably something up. Right? You would maybe look for a string hanging from the ceiling, or look for a little hand holding up the pencil. Okay? You probably wouldn't just shrug your shoulders and say, well, it is the way it is. Now, foreshadowing our discussion of anthropics a little bit, you might have a very different attitude about it if, in looking more carefully at the table, you notice that the pencil was surrounded by all sides by grenades and deadly bombs of all varieties, such that if a pencil fell over a little bit, it would set them off and blow the entire room up. If you saw that, then a totally different kind of explanation would also occur to you. Right? Not that there's a pencil hanging from the ceiling or a little hand holding it up, but that there's lots of rooms out there, and most of those people are very unfortunately very dead. Okay? And only in some of them, completely accidentally, is it not so, and there you are. But this is not a tautological or specious or stupid argument, because in order for you even to be able to run it, it had better be true that the bombs are there. If there are no bombs there, you can't rely on this argument. You have to see something about your existence that ridiculously sensitively depends on what looks like the fine adjustment there. If you don't find such a thing, you can't run this argument. Okay? If you do, you might be able to. But nothing stops us from doing this. We can say, the pencil is just standing on a tip within 10 to the minus 120 degrees of vertical, proceed. Right? And that's what we actually do, and we have no problems, and all the rest of physics works. Now, there's a very similar issue with the question of why there are big things in the big universe, which, as we just reviewed a second ago, has to do with the question of why gravity is weak. And I won't review this in much detail, but the question of why gravity is weak ultimately has to do with why the masses of the elementary particles are so much smaller than the Planck scale. And the masses of some of the elementary particles, we have a good understanding why they're small compared to the Planck scale, but other ones we don't. Particles like the electron, for example, this is a horrible metaphor that I apologize for. I promised myself never to use it again, but here I am using it again. Anyway, there's this stupid metaphor for the Higgs, for how particles get their mass by wandering through the universe and banging into this background Higgs field, which is utterly and completely false. But anyway, in that metaphor, the difficulty is that the Higgs field is itself drastically fluctuating quantum mechanically. And so while the typical length scale between these collisions that's needed to accommodate the observed mass of the electron is around this weak scale, 10 to the minus 17 centimeters, we would expect violent fluctuations in the Higgs at around the Planck length, 10 to the minus 33 centimeters, and that would make everything 16 orders of magnitude heavier than it is. And that would be a disaster, right? Okay, everything would collapse into a black hole. And once again, so not only does having a big universe demand this gargantuan fine-tuning of 1 part in 10 to the 120 or so, or at least 1 part in 10 to the 60, but having big things in the big universe requires a fine-tuning of about 1 part in 10 to the 30 in our parameters. Let me try to describe this in a more technically correct language, because you might find it illuminating. The second question of why their elementary particle masses are small compared to the Planck scale is related to why why gravity is weak is related to the question of why the particle masses are so small compared to the Planck scale. And let's ask the question for a familiar particle like the photon. Well, we think the photon is massless, right? But why is it okay the photon is massless? That's really good. That's 0 compared to the Planck scale. So how does it manage to stay massless? After all, the photon barrels through the vacuum and interacts with all these virtual fluctuations of all varieties. Okay? So there's what you might call the totalitarian principle in quantum mechanics, that everything that can happen must happen. So why doesn't the photon pick up a mass, just an inertial mass from all these complicated interactions with the vacuum? And the reason why the photon doesn't pick up a mass is very simple but deep. It's because 2 is not equal to 3. Okay? A massless photon, the photon has spin 1, but because it's massless, it only has 2 degrees of freedom. If its spin is moving in this direction, if it was massive, it would have 3 spin degrees of freedom. Whatever direction it was moving in, you could go to a frame in which it was at rest, and if you saw it spinning this way, by tilting your head, you would see it spinning in every other possible direction, and you would conclude that it has 3 degrees of freedom. But because it's massless, you can't do that. You can't go to a frame where it's at rest, you can't tilt your head, and so it only has 2 degrees of freedom. This is a deep and very important fact about, again, relativity and quantum mechanics, both together. 2 is not equal to 3. And that means that no small perturbation to the photon can all of a sudden make it massive, because you can't invent a degree of freedom out of nowhere. Okay? So you cannot, there's no continuous change you can do. The massless and massive photon are discontinuously different from each other. It's not obvious ahead of time, but it's true. Our difficulty is that the Higgs particle, remember I told you, one of the exciting things about it is the first particle of spin 0 that was discovered, right? We got to add that 0 to our list. And the problem is that exactly for particles of spin 0, 1 is equal to 1. Okay? There is no difference in degrees of freedom between a massless and a massive spin 0 particle. And therefore, exactly the analogous question we had before would lead us to suspect that the Higgs should be as heavy as it can possibly get. And these quantum fluctuations that we talked about would naturally want to put it to the shortest possible distances we can talk about. Okay. Now, of these 2 problems, the question of why the universe is big obviously seems, the cosmological constant problem obviously seems much more severe than the Higgs problem. It's numerically much more severe. It's more important for the most 0th order issue of making the world big to begin with. But let's put it aside for now and pursue the second question. This was an attitude that as I said, many theoretical physicists took. Let's just ignore the cosmological constant problem. Something will solve it. Some magic will solve it someday. Let's ignore it for now. And surely we're going to have a solution to the second problem, the wise gravity weak problem, the hierarchy problem. And here, if I say another thing about what's so remarkable about having discovered the Higgs, is that we've in fact never seen something like the Higgs particle in a state of nature before. Our universe, well, we have one vacuum of our universe that we study in particle physics, and it's governed by these basic laws of quantum field theory. But in the lab, we can engineer tons of other kinds of quantum field theories that are qualitatively seem very similar. Okay? They have local interactions at sufficiently large distances. They're described by quantum fields in a very similar way. And so these are things that our friends in solid-state physics do for a living. They engineer zillions of so-called effective theories like this all the time. So we can ask, in the lab, do we ever find a situation where you see something like the Higgs particle lying around? The answer is never. Not once has it been seen in a state of nature. Okay? Sometimes it's seen. In fact, if you're trying to describe what happens to a system as you bring it close to a phase transition, let's say liquid to gas phase transition, or magnetic phase transition, as I've shown in this example. Sometimes, as you get very close to the phase transition, there's an effective description of the physics that has something very much like the Higgs particle in it. But that only happens when there's an experimentalist on the outside twiddling the dials, bringing it by hand close to that phase transition. Okay? So this is just a bare fact, when we've seen something like the Higgs in nature before, it's been explicitly associated with fine-tuning. Somebody on the outside finally adjusting the dials to see it happen. And conversely, the fact that we haven't seen just lying around, you pick up a hunk of metal and you see it, is it described by something that looks like the Higgs at long distances? No, that's validation of this idea that everything that can happen does, and if there's no reason for it to be there, and if there's no fine-tuning, it isn't there. And yet, that's what we seem to see in our universe. Okay? So that's what's so surprising and remarkable about having discovered the Higgs. So there's this doctrine, the doctrine of naturalness, that says that if we find a situation where it seems that some phenomenon requires very fine adjustment of the parameters in order to arise, then there's something wrong. We're missing a part of the physics, and we should extend our picture of the physics in such a way as to make what appears to be unnatural, natural. What appears to be fine-tuned have an explanation. Okay? That's the analog of finding the string hanging from the ceiling or the pencil or the hand holding up the pencil. Right? And if you don't seem to see that, if it seems that there's fine-tuning, you say there's some tension with the idea of naturalness, or there's a naturalness problem. Okay? In this form, and applied to thinking about the difficulties with this fine-tuning issue with the Higgs, the idea of naturalness was suggested by Ken Wilson and Gerardo Tuft in the 1970s. But as I'll mention in a second, this is a very old idea that's had a great track record, especially in the past 100 years. Okay? This kind of question has appeared actually 3 times in the last 100 years. 3 times in the last 100 years we've had very similar naturalness problems, and every time they've been solved in precisely this way. Some new physics comes in just as needed in order to avoid the apparent fine-tuning and give a dynamical explanation for what otherwise appeared to be a fine-tuning. So I want to give you one example of this, because this idea of naturalness has worked beautifully. And this is a little over 100 years ago. People like Abraham and Poincaré and Lorentz were very worried about the infinite self-energy of the electron. They thought the electron was point-like, and if you calculate the energy stored in the electric field around the electron, you get infinity. So if you cut that, if you make an estimate saying the electron has some size or somehow changing the logic of the discussion at some scale, and you ask what that scale needs to be in order for the energy in the electric field to be comparable to the mc squared of the electron, you get a formula called the classical radius of the electron, and here it is. It's around 10 to the minus 13 centimeters. So Abraham and Poincaré and Lorentz argued that some new physics has got to happen by 10 to the minus 13 centimeters in order to avoid this problem. They said if it doesn't happen, if let's say the electron continues to look point-like to 10 to the minus 15 centimeters, then there's 100 times bigger energy in the electric field around the electron that somehow must be compensated by some fine adjustment, maybe of some negative mass of the electron to a part in 100. And that's crazy. So they said something new should happen. Something new should happen by around 10 to the minus 13 centimeters. They even had a concrete model in mind for what that new thing should be. They made the electron a shell. They tried to give it a finite size. That model was wrong. It had lots of internal theoretical difficulties, and it was wrong. But their basic logic was correct. In fact, it was more correct than they realized. This solution, this problem had a much more radical solution. It involved the discovery of both relativity and quantum mechanics, and the picture that we talked about before. The electron is actually surrounded by this virtual cloud of electrons and positrons popping in and out around it. That means that the electron is no longer point-like, effectively point-like, on a distance scale which is the Compton wavelength of the electron. Okay? And it's a very nice estimate to parametrically look at the Compton wavelength of the electron and positron compared to this classical electron radius. You discover that it's actually 137 times bigger. Okay? So not only were they right, they're, as I said, more right than they realized. The physics did change. It changed 137 times earlier than it had to change in order to solve this problem. Okay? And 2 more times, something very analogous has come up in the last 100 years and has had this character. So that's one of the interesting features of naturalness problems. Okay? You have to say that the new physics comes in at a given scale or earlier. And if it doesn't, then you start getting indication for some fine-tuning. But 3 times in the last 100 years, when this kind of problem has come up, it's had the sort of solution that people were expecting. Okay, so, well, what could it be in this case? Could it be anything? Well, what we can do as theorists is go back. We don't have many tricks, right? We know what the world can do at long distances. At sufficiently long distances. This is a problem that's showing up at sufficiently long distances. Sufficiently long distances here means that distance is long compared to the Planck scale. This difficulty with naturalness is something showing up at around, distances roughly comparable to what we're probing in experiments today, well huger than the Planck length. So there's not that many things we can do. We have one toolkit. We can go to our toolkit and say, what can we do that we haven't done? And there's one obvious gap. There's one thing that the world could have that's compatible with the basic laws of relativity and quantum mechanics that we haven't seen it do. And that's associated with this last possibility of having a particle of spin 3/2. Having a particle of spin 3/2 is possible, but it's only possible if the world has a very special symmetry that I'm sure all of you have heard of supersymmetry. And let me just give you a qualitative idea of what supersymmetry is. So if you just describe it like this, it looks like another fanciful things that people pull out of a hat for what could be going on. But I emphasize that the real reason theorists are excited about supersymmetry is it's the last thing nature can do compatible with its basic principles that we have not yet seen it do. Okay? If we see that, then it's done. We know that nature can do everything it can do, and then all the essential mysteries get pushed up to Planckian energies as well as cosmological questions, as we'll talk about more tomorrow. But one way of talking about supersymmetry is by adding extra dimensions to our universe. People like talking about ordinary extra dimensions, which are a lot like ours, but maybe they're curled up or warped or something in some way. Those are really boring, actually. Those kind of extra dimensions are extremely boring. They're not conceptually very interesting. There's just more of the same as what we have now. Supersymmetry is something much more conceptually interesting, because it says that in addition to our ordinary dimensions, we have these other dimensions, but the distances in these other dimensions are measured not in ordinary commuting numbers, but in anti-commuting numbers. Okay? In a sense, supersymmetry makes space-time more quantum mechanical by making it possible to measure distances in space using quantum variables that we can't talk about classically. And since they're anti-commuting, so if there's an x and y distance in the quantum direction, dx dy is negative dy dx, and that means that dx and y squared is equal to 0, and that means you can't take more than one step in the quantum dimension. Okay? D squared is equal to 0. Okay? Imagine doing any kind of Taylor expansion for a function that would depend on ordinary space as well as the quantum space. You can't even have more than one coefficient. Okay? You can't take more than one step in the quantum dimension. And that's fascinating because this is a mechanism, in fact, the only robust mechanism we've ever discovered to remove violent quantum fluctuations of the vacuum. How does it work? Imagine taking our box where we had these bigger and bigger fluctuations, which are getting bigger and bigger as we go to smaller and smaller scales. The symmetry part of supersymmetry tells you there's got to be perfect symmetry between the ordinary and the quantum dimensions. So you're fluctuating more and more and more and more. So you get down to small enough sizes where you actually see these quantum dimensions are there. But since there's got to be just as much symmetry between the ordinary and the quantum dimensions, if you're violently fluctuating in ours, you've got to be violently fluctuating in it. But you can't violently fluctuate in it. You can't even take more than one step, never mind go back and forth and back and forth and back and forth a zillion times. So how is this mystery resolved? It's resolved by no longer fluctuating in our space either. Okay? And this is actually not a cartoon. I mean, this is a bit of a cartoon, but it's 90% close to the actual best technical argument for how supersymmetry solves these problems. I say it this way so you understand that this problem with the violent quantum fluctuation of the vacuum is it's a structural one. It's sort of hardwired into having particles and antiparticles and quantum fluctuations, the uncertainty principle, and all the rest of it. If something is going to remove this problem, it should be structural and big. Supersymmetry is something structural and big, and it removes the problem in this way. Okay, so that's wonderful. And this kind of line of argument has worked, as I said, for the last 100 years. So you should make a prediction. Supersymmetry or something like it, some kind of natural physics, something, the hand holding up the pencil, should be showing up in order to remove the difficulty with the fluctuations of the Higgs. And now, we've gotten to the energies where we've made the Higgs, and we're going to higher energies at the Large Hadron Collider today. But for 20, 30 years before that, we've been looking indirectly for effects of new physics that could be coming in at this scale. And the entire time, in fact, it was disturbing already 20 years ago, but it's getting more and more disturbing now. And this is something which seems new about this problem, unlike the 3 previous times when it worked. 3 previous times when it works, the new physics not only showed up, it showed up earlier than it had to. Okay? And now we seem to be in the situation where we even discovered the Higgs, but we haven't seen anything else yet. Okay? If this argument is correct, even applied to the Higgs, forget about the cosmological constant, even applied to this more mundane and down-to-earth set of questions involving the Higgs, where is everybody? Where is all the physics that should be there to stabilize the quantum fluctuations of the Higgs? And in fact, it's this broad idea of naturalness which is being put under moderately more pressure by the results of the Large Hadron Collider so far. In fact, many of us have been, people ask me, are you worried about whether supersymmetry will be discovered at the LHC or not? And I tell them, given what we've seen so far at the LHC, I'm not particularly more worried than I was before. That's because I was already somewhat worried beforehand. Okay? Not horrendously worried, but it's disquieting. It's a little funny. It's, again, not like the previous cases where it just worked bang on, right? Here, you're starting to make excuses, right? We never had to make excuses before. And it's this, at least in the last 100 years, okay, when this kind of problem came up. And it's not supersymmetry itself. That's just a sort of best example of what such physics should be. It's this whole broad idea of naturalness in this very concrete guise of dealing with the Higgs that's being put under more pressure by the LHC. And so it's therefore worth remembering that the idea of naturalness has also failed dramatically. If you go way back, it's not obvious that this example is actually relevant to our life today, but it's an interesting example. If you go way back, naturalness caused the ancient Greeks to take a big wrong turn in thinking about the solar system. In fact, Aristarchus, as probably many of you know, Aristarchus had the heliocentric model of the solar system already in many hundred BC. I don't remember when it was exactly. He worked out the distance from the Earth to the Sun. He understood all these things very beautifully. It was an enormously large distance, the distance from the Earth to the Sun. But he still proposed the heliocentric model with everything going around the Sun. And his colleagues rejected this idea. They said, well, this makes a prediction. You should see parallax of the distant stars. And you can't see parallax of the distant stars with your naked eye. Okay? So Aristarchus said, well, those things must be even much further away than the Sun. And his colleagues said, lucky for you. That's great. Yeah, sure. Already this thing is really far away and we're really close to it and we're vastly further than everything else just so your model survives. Yeah, great. That sounds right to us, right? So their idea of naturalness caused them to reject the correct theory. So much was not known back then. People didn't understand the dynamics. They didn't understand that gravity could make some things close to each other and other things far away. Okay? They didn't understand tons of things. But this basic idea of what was natural and what was not led them to reject the correct idea. Now, if we go a little further down, these problems about whether or not we're seeing new particles yet associated with the Higgs, they're starting to give us evidence already from the null results for seeing new physics at the LHC so far, that there may be fine adjustments in the parameters associated with the Higgs at the 10% level. Not something much worse than that. There's something at around the 10% level. Okay? So should we be so exercised about that? Maybe it's not a big deal at all. In fact, if we go down one more energy scale from where we are in particle physics down to nuclear physics, there are these very curious accidents and well-known accidents in nuclear physics. For example, the binding energy of a neutron and a proton in the deuteron, it's smaller than you would expect it to be. That's maybe not so severe. That's about a 20% accident. But a more remarkable thing is if you take two neutrons, they're not bound. But the amount by which they're not bound is ridiculously small compared to the typical energy scales of nuclear physics. It's about a 1% accident. Okay? They come with a hair's breadth of being bound and they're not. And this is just a fact, right? You just go down one energy scale down, there it is. There seem to be these 20%, 1% level tunings just there. So maybe, it is what it is. Okay? So maybe maybe these accidents can happen. So those are reasons to be suspicious of naturalness. But of course, there's a much bigger reason to be suspicious of the idea of naturalness. And so we avoided it all this time, but let's come back to thinking about the cosmological constant problem. Okay? The energy scale associated with the cosmological constant, if we apply exactly the same, I mean, it's a minuscule, the observed value of the cosmological constant is like the energy density of the universe today. And it's around 1/1000th of an electron volt in every cubic millimeter of space. Okay? It's a minuscule amount of energy. But if we use this naturalness argument to say, well, something has got to be controlling the violent quantum fluctuations to some scale, and we don't want it to go much past the length scale associated with the problem where we'd have to start tuning even a little bit, that makes a prediction for where the new physics should show up. And that prediction is that the new physics should show up at around the millimeter scale. Okay? And we can all do the experiment. No, there's no new physics in a millimeter. Okay? In fact, you might imagine that we are creatures that were made out of atoms, not our atoms, but other creatures made out of atoms, that were 10 kilometers big. And they're living in our universe. And they look around. They're very smart. They discover cosmology and all the rest of this stuff. And they see that the universe is expanding and accelerating. They realize there's a cosmological constant problem. And they're like, what could it possibly be? And their brightest theorists sit around thinking and they say, I know, the world is supersymmetric at the millimeter scale. Supersymmetry removes violent vacuum fluctuations, and it could also solve this problem in principle. Okay? In order for it to solve the problem, the universe would have to be supersymmetric at the millimeter scale. Now, the millimeter is a tiny distance scale for these creatures. Remember, the atoms are 10 kilometers big. So they build the large millimeter collider in order to probe, and surely no one has come up with any idea other than supersymmetry, and it's not there. Okay? Supersymmetry could have solved this problem, and it did not. Okay? And it's not just this or that mechanism. Okay? Just the basic logic of naturalness leads to an incorrect prediction in this case. Okay? We just all did the experiment. Now, I should say, as little caveats, that the people say, well, maybe only gravity's got to be affected at the millimeter scale because this is a gravitational problem. And this was an idea that no one could make any sense of theoretically, but still, you think, well, maybe gravity somehow shuts off at the millimeter scale. We haven't measured gravitational forces, or we hadn't 10 years ago, 15 years ago, at distances much smaller than a millimeter. So maybe gravity miraculously shuts off as you get down closer to the millimeter scale. As I said, no one could make any working model of this, let alone make it solve the cosmological constant problem, but it's a qualitative prediction. And even qualitative predictions are good because that spurs experimentalists to go look. Experimentalists have gone and looked. They've probed gravity down to the 30 micron scale. Nothing's doing. Okay? So even this qualitative idea is just wrong. Right? So there's nothing new at the millimeter scale, either non-gravitationally, gravitationally, nothing. The idea of naturalness makes a manifestly incorrect prediction in this case. Now, does it mean that it's obviously crap and we shouldn't even think about it for anything else, like the hierarchy problem or anything else? Well, no, because you could have used, it's not the way the history happened, but a sophisticated theorists of the early 1900s might have appreciated something like the cosmological constant problem and made fun of people trying to solve the electron self-energy problem by saying, we have this much more severe cosmological constant problem. You guys are wasting your time. And it would have been a stupid thing to do, okay? Because that problem did have a natural solution. You can always use the history of physics or science in general to illustrate any polemic point you want to make, okay? And we just don't know ahead of time. That's, I think, what I want to stress here. We just don't know the way we don't know which way this is going to go. But we have reasons to be suspicious of the validity of these naturalness arguments. Okay. Well, we'll talk about it more tomorrow, but as you all know, one completely orthogonal possibility for what could explain these naturalness problems is this picture that we're actually a tiny part of a vast and mostly lethal multiverse, and we live in the only place we can live. Constants change from place to place. The value of the cosmological constant changes from place to place. Mostly the universe in those places, a la the famous argument of Weinberg, is accelerating so quickly that it blows apart structure before it has any chance to form. In a few tiny little pockets, the cosmological constant is small enough that any structure can possibly form, and obviously we're going to find ourselves there. And that's no more mysterious that we find ourselves there than that we live on a little rock called planet Earth, occupying a volume that's 10 to the minus 60 of all of the volume available to us in our Hubble patch of the universe. That's also not a pressing problem of theoretical physics, as we're not going to live in the middle of emptiness. We're obviously going to live where there's some structure. Okay? And again, for this argument to have any traction, it had better be correct that small variations of the cosmological constant lead to tremendous changes in what the macroscopic universe looks like. And indeed, as Weinberg famously argued, that is the case. If we make the cosmological constant in our world a little bit bigger, it would be a little bit bigger than it is, maybe a factor of 10 or 20 or 30 bigger than it is, then the universe would just be empty. So it's a completely different possibility. It raises all kinds of thorny conceptual questions, again, not polemical questions about is it science or not. I could care less about whether it's science or not at this point. It raises really thorny theoretical questions about how to even make sense of it conceptually. Once we figure out whether it makes sense conceptually, we can ask whether it makes predictions, whether it stands on its own 2 feet, whether we can confront it with experiment. But at the moment, it's not in my view, it's not a question for polemics or even philosophy of science. It's a question for theoretical physics to try to make sense of this strange picture of the multiverse. So we'll talk about it at greater length tomorrow. But these are the kinds of choices that we have. Will nature be natural or unnatural? Will it be something like supersymmetry or the multiverse in this direction, or even something that we haven't thought of yet? We don't know, but we are going to get help from experiment, at least for the question of naturalness for the Higgs. If we see the Higgs and nothing else at the LHC, it'll give us some indication of a fine-tuning at about the 1% level. Right now it's about the 10% level. If we continue to see the Higgs and nothing else till 2020, then we'll have evidence for tuning at around the 1% level. And that'll still put us in a rather uncomfortable situation, I have to say. It's definitely not like it's happened before in analogous situations, but we have also seen 1% level tunings elsewhere in nature. We just talked about one. We saw these accidents in nuclear physics. That's about a 1% accident. We can talk about that later. There's silly things like the fact that the moon eclipses the sun almost perfectly. That's, as far as I know, has no anthropic reasoning whatsoever. I like to call it the Miss Virgin Anthropic principle. It doesn't help anyone, but it did kill an awful lot of Mayan virgins. Okay, okay? That's just an accident. That's just about a % accident. So these % level accidents happen. And so it could be that if we see the Higgs and nothing else at the LHC, it'll give a significant push, not to believing that there's a multiverse or something like that, but it'll give a significant push to seeing that there is fine-tuning. There really is fine-tuning in some fundamental parts of physics, but I don't think it would be a knockout. To really make it a knockout, we'd have to go to even higher energies and continue to see nothing but the Higgs. Okay? If we go to 10 times higher energies and continue to see nothing but the Higgs, then we'll have evidence for fine-tuning at the 1 part in 10,000 level. That's something that we have not seen like anything like it in nature, other than perhaps the cosmological constant. Okay? But it would be something that would clearly separate the Higgs from the rest of these sort of crappy accidents to something rather singular and different and looking more like the cosmological constant. But that's, I think, the sort of thing that we're going to have at play. By 2020, from the LHC, we could get strong evidence that there is naturalness. At the 11th hour, we could actually see all these particles that we expect to be there in order to make things natural. Okay? It's not a big deal that they haven't shown up yet. It's a little disquieting, but it's by no means a huge problem. So we could see that. That would be wonderful. It would be big new principles. It would still leave us greatly in the dark about the cosmological constant. It would shed no light on that question. We could start getting more of a push towards the picture where it's unnatural. And in many ways, if we continue to see the Higgs and nothing else, in many ways, that's a bigger paradigm shift. It would start making the Higgs look more like the cosmological constant, but then the real question is, how tuned is it? Are we going to be content with seeing that it's tuned at the % level? There are some intermediate possibilities that I'm fond of, but which I won't talk about yet. But I'll just end with this, just as a segue to our discussion tomorrow. So, are we a tiny part of a vast multiverse? We'll talk about the basic picture more tomorrow, and I'll repeat what I said a moment ago. That to my mind, at least it's premature. It's prematurely a philosophical question, although it might be interesting for philosophers to think about. But we have problems even calling this a theory. It's not even a theory. It's barely a caricature of what a future theory might look like. And the issues are not of polemics, but of theoretical physics, trying to make sense of it. And as we'll see tomorrow, one of the big problems with this entire picture is the fact that our own universe is accelerating today. And the acceleration of our universe today means that all the rest of this multiverse, the part that's supposed to be out there, is out of causal contact with us. And it doesn't appear that the regions are out here, and it appears that light from them can never get to us. No signals from them can ever get to us. And so it looks like that multiverse outside our cosmological horizon is in our head. Okay? Now, you might think, oh, that's obviously stupid then. Haven't you guys learned anything? You shouldn't talk about these things that can't in principle affect you. But not so fast. because being inside an accelerating universe like this is a lot like being inside a black hole rather than outside a black hole. And we've learned a lot in the last 10, 20 years that there are ways of talking about the things that are inside a black hole, which are in some scrambled way contained in things that eventually come out of a black hole. So just because they're not classically in causal contact with you, just because of that, it doesn't mean that there isn't some reasonable sense in which you can imagine that they actually exist. Okay? So it's confusing. We don't know either way, but that's what I said. The question is one of theoretical physics, and it brings together in one place every major conundrum associated with the first set of issues that I mentioned right at the beginning with the challenges of the 21st century. The end of space-time and possible cosmological extensions of quantum mechanics. The hardest questions we have to face in physics anyway, quite apart from these anthropic considerations. Those hardest questions we have to face anyway come up at order 1 in order to start even addressing this issue. And in fact, these very biggest conceptual puzzles involve quantum mechanics and cosmology together with the idea of emergent space-time. That's what we'll spend tomorrow talking about. Thank you.